Remember, you're working to answer this lesson question. What does it mean for statements to be logically equivalent? Now, so far you've learned about conditional statements, that they have a hypothesis and a conclusion. Now you'll work with conditional statements to derive the inverse, converse, and contrapositive. Let's take a look at this conditional statement. If an angle measures 50 degrees, then it is an acute angle. Now notice that this statement has a hypothesis and a conclusion. Now we're going to take a look at the converse. The converse switches the hypothesis and the conclusion of the conditional statement. So instead, the conclusion is going to come first and the hypothesis will come second. Now, if we're using sentences, we may need to change some grammatical structures, but the ideas are switched. Let's take a look at this converse. If an angle is an acute angle, then it measures 50 degrees. Notice that the original hypothesis becomes the conclusion of the converse, and the original conclusion becomes the hypothesis of the converse. Now let's also think about whether or not this is a true statement. So we'll use a counter example. Here I'm going to use 70 degrees as an example. If an angle is an acute angle, well, 70 degrees is an acute angle, then it measures 50 degrees. Well, this angle is 70 degrees, so this statement actually is false. We can't assume that a converse statement is going to be true or false in all instances. It'll depend on the situation, so we need to use our own reasoning when determining whether it's true or false. Now let's take a look at another statement, the inverse. The inverse negates the hypothesis and the conclusion of a conditional statement. So the inverse means taking the opposite or adding not. So in this case, we'd say if an angle does not measure 50 degrees, then it is not an acute angle. So let's take a look at the inverse. If an angle does not measure 50 degrees, then it is not an acute angle. Now notice here that the hypothesis from the original conditional statement is still stated first, it's just negated. And the conclusion from the original conditional statement is still stated second, but here again it's negated. Let's use a counterexample to figure out whether this is a true statement. So again, I'm going to use 70 degrees as an example. If an angle does not measure 50 degrees, 70 degrees is not 50 degrees, then it is not an acute angle. Well, 70 degrees is an acute angle, so this statement is also false. Again, we can't assume that an inverse statement is true or false in all instances. Again, it'll depend on the situation, so you need to make sure you use your own reasoning. Now you're going to work to identify a converse and an inverse. So we took a look at this conditional statement and identified the converse and inverse. Now let's look at a contrapositive. A contrapositive switches and negates both the hypothesis and the conclusion of a conditional statement. So here is the contrapositive of our original conditional statement. If an angle is not an acute angle, then it does not measure 50 degrees. Notice that the hypothesis and conclusion were switched from our original conditional statement, and both statements were negated. Now, we can think about this also as a combination of both the converse and inverse. You could begin with the converse statement and then negate both parts. Or you could begin with the inverse statement and then just switch both parts to come up with your contrapositive statement. Let's also think about whether or not this contrapositive is true. If an angle is not an acute angle, so if it's an angle that's 90 degrees or higher, then it does not measure 50 degrees. Well, any angle that's 90 degrees or higher does not measure 50 degrees, so this is a true statement. Now you're going to identify a contrapositive statement. Let's take a look at this example. Here's a hidden conditional statement. We will have a picnic if it does not rain. Now we do have this keyword here, if, so it indicates that there is a hypothesis here, but we don't have a then, although there still is a conclusion that's given. Let's go ahead and rephrase this though as a conditional statement. If it does not rain, then we will have a picnic. Notice that we have if and our hypothesis, and then and our conclusion. Now let's take a look at the converse. If we have a picnic, then it will not rain. Notice that we have switched the hypothesis and conclusion from our conditional statement. And here's the inverse. If it rains, then we will not have a picnic. Now in this inverse, we've negated both the hypothesis and conclusion from the conditional statement. Notice that we write if it rains. We could have used a double negative and said if it does not rain, but it sounds more grammatically correct to say if it rains. And finally, let's take a look at our contrapositive. If we do not have a picnic, then it will rain. So both statements have been switched and negated. Now, I want to point out that this is a true statement. You may think, well, you can't control the weather. How is that? But remember, we're focusing on this situation. These people will have a picnic if it does not rain. The only time they would not have a picnic is if it does rain. So in this case, this contrapositive is true. So now you're going to try one. We can represent conditional statements using Venn diagrams or create conditional statements based on diagrams. Let's take a look at this example. If a triangle is equilateral, then it is a regular polygon. Here's a Venn diagram that represents that conditional statement. So we have a circle here that represents the set of regular polygons, which have all congruent angles and all congruent sides. Some examples might be a square or a regular pentagon. We also have a circle here in orange that represents the set of triangles. Now, some triangles are not regular polygons, like right triangles or scalene triangles. Now, the intersection of these two sets here represents equilateral triangles. They're the only type of triangle that is also a regular polygon. So this Venn diagram represents the conditional statement, and we can also make other statements based on this Venn diagram. I can make the statement that some triangles are regular polygons. Now this statement is supported by the Venn diagram because I can see some triangles that are not regular polygons, like these two here, but there's also a type of triangle here that is a regular polygon. I could also think about the converse to our original statement, which would be if a polygon is regular, then it is an equilateral triangle. I can also see from the diagram that this is not true. I can see here that a square is a regular polygon that is definitely not an equilateral triangle. Let's take a look at another example. So here's a statement. All right angles are congruent. This is actually a hidden conditional statement. We could rephrase this as, if angles are right angles, then they are congruent. And here's a Venn diagram to represent that statement. So this orange circle here represents the set of right angles. And this blue circle here represents the set of congruent angles. We can see here that the orange circle is completely inside of the blue circle. In other words, this set of right angles is also a part of this set of congruent angles. So now you're ready to write a conditional statement from a Venn diagram. I hope you're starting to think about how you will answer your lesson question. What does it mean for statements to be logically equivalent? Now, so far, you've learned how to write converse, inverse, and contrapositive statements based on a conditional statement and thought about whether those statements are true. Now, in mathematics, we'll often use symbols to represent ideas, to save time, and to write more compact mathematical sentences. Next, you're going to learn how to use letters like these in order to represent logical statements. Let's begin with this conditional statement. If an angle measures 125 degrees, then it is an obtuse angle. Notice here we have our hypothesis and our conclusion. Now we're going to represent this symbolically. We'll use letters to do that. We're going to use a P to represent the hypothesis and a Q to represent the conclusion. Let's see how this applies to the types of statements you've learned about. We'll begin with the conditional statement. So we have our hypothesis, if an angle has a measure of 125 degrees, and our conclusion, then it is an obtuse angle. Here's the symbolic statement for this. This will read as, if P, then Q. Now let's take a look at the converse. If an angle is obtuse, then it has a measure of 125 degrees. So the symbolic statement for this would be, if Q, then P. Notice how we switched the hypothesis and conclusion. Now let's take a look at the inverse. If an angle does not have a measure of 125 degrees, then it is not obtuse. Now notice that the order of the hypothesis and conclusion is the same as in the conditional statement. So what we'll do is we'll use this tilde symbol here to represent the inverse. So this is going to read, if not P, then not Q. All right, the last one, our contrapositive. If an angle is not obtuse, then it does not have a measure of 125 degrees. So we're going to have a symbolic statement here that reads, if not Q, then not P. So now see if you can apply what you've learned about symbolic statements. Let's take a look at the truth values of conditional statements. We can use a truth table like this one to break down whether a conditional statement is true or false based on its parts. Let's take a look at what's given. P is, I get a raise. Q is, I buy you a ring. So the conditional statement is, if I get a raise, then I will buy you a ring. So think about this like a promise. Let's go ahead and apply that now to the truth values. So what if both P and Q are true? I got a raise and I bought you a ring. Well, I kept my word, I kept my promise. So in this case, the conditional is true. Now what if P is true, but Q is false? I got a raise, but I didn't buy you a ring. Well, in this case, I didn't keep my promise. So this conditional is false. What if P is false and Q is true? I didn't get a raise, but I bought you a ring anyways. Well, I didn't say what I would do if I didn't get a raise, so the validity of this statement can't be judged. But I didn't break my promise, so the conditional is true. And finally, what if both P and Q are false? I didn't get a raise, so I didn't buy you a ring. Well, based on this reasoning, the conditional would be true. Now, the only time a conditional statement is false is when a true statement implies a false one. That's important to keep in mind. So a truth cannot imply a false. Now you're going to determine a truth value. Remember that a conditional statement is only false when we have a truth implying a false. Now we saw that here when P was true and implied Q, which is false. Let's now apply this to the converse. So we'll begin with the Q this time. Now if both P and Q are true, then the converse is true. But if we have Q, which is false, implying P, which is true, then the converse is true. But if we have Q, which is true, implying P, which is false, then the converse is false. If both Q and P are false, then the converse is true. So notice here that the converse is false only if Q is true and implies P, which is false. Now we're going to take a look at the inverse and contrapositive. And you'll see that in these two columns, we have P and Q negated. So the true and false have been switched for each. So let's find the truth statements for the inverse. Now, if we have the inverse of P as false and the inverse of Q as false, well, then the inverse is going to be true. Now, if the inverse of P is false and implies the inverse of Q, which is true, that's true. But if the inverse of P is true and implies the inverse of Q, which is false, then the inverse is false. And if both are true, then the inverse is true. Now, for the contrapositive, if both the inverse of Q and the inverse of P are false, then the contrapositive is true. If the inverse of Q is true and implies the inverse of P, which is false, then the contrapositive is false. But if the inverse of Q is false and implies the inverse of P, which is true, then this is true. And if both are true, then the contrapositive is true. So notice here that the inverse and the contrapositive are false only if a truth is implying a false. So now that we've looked at this table, I want to show you one more that illustrates an important point. So here we have all of our statements listed out. You'll notice that the truth values for the converse and the inverse are the same. And the truth values for the conditional and the contrapositive are the same. So here's an important thing to keep in mind. Two statements are logically equivalent when they have the same truth values. So we can see here that the converse and inverse are logically equivalent, and the conditional and contrapositive are logically equivalent. Now you're going to think more about logically equivalent statements.